So far, we have applied Laplace transform to analyze and to solve ordinary differential equations, which we could have solved using the other methods, like the ones you learned last semester in 1 and 2. But now comes the case where ODEs will become more difficult and will be much more tricky to solve using the previous approaches. And that is often the case of interest in applications to study electric circuits. So what if somebody suddenly turned on and off things midway? So there will be sudden changes in the input. Before we can look in more detail at these equations, we need to learn a new concept called causal functions. A causal function is a function of a single variable which appears at some time and which does not exist until that time, which means that it's 0 up to given time. Oftentimes it's just 0, but sometimes it can be some positive fixed time, say 10 seconds. So there was nothing before 10 seconds and then something happened. Let's look at some of the examples when this causal function appears. Well, you've already seen one example. It's a unit step function. So in this case, that shift is not present, so the a equals 0 here. So for t less than 0 it's 0, and for t greater than 0 it's 1. And here we go, right? So that is function equals to 1. Or equals to 0, right? And the switch happens at time equals 0. And you've seen that these sometimes denoted by h or h0 because it's a shift that it switches on at time 0. And it's named after Oliver Heaviside, who was an English mathematician and engineer, as well as physicist. But we can also have a shifted version of that unit step function, which only switches on at a given time a. And that's a shifted version, where at time equals a, it suddenly switches on. Well, this is probably more or less straightforward so far, but we can use the step function to introduce much more interesting functions. And then we can make this function switch on and off. Or we can even make a shifted version of the function and then switch it on and off. So let's look one by one at these examples. For example, here you can see an example which is a function, a parabolic function, which in general looks like that, right? And so on. And we applied a unit step function, which is 0 up to time 1, and then it switches on. So that is the u t minus 1, and that is t squared. And if we multiply these two functions, we will get the exact shape you see here, which does not exist before that point. So that is a function t squared times unit step function shifted by 1 to the right. And that, as you see, it discontinues, right? It jumps from 0 to 1 at time equals 1. That's one example where we combine a function which is continuous and a function which is not continuous, like the unit step function. Another example, we can look again at the parabola, but this time parabola is shifted or delayed. So the parabola here looks like that. So that is t minus 1 squared. And then you also applied again a unit step function which only switches on at time t equals 1. And if you multiply these two functions, you will get that function. Right? And that will be described by t minus 1 squared times unit function t minus 1. So again, it's shifted to the position 1. Let's move on. We can see already that in general we can make a function which appears to be switched on at time a as if it was actually time 0. So you can say that that is a generic function f multiplied by the unit step function, which can be described as function itself for times greater than a and 0 for times less than a. And we also can do even more fancy things. We can switch on at one time and switch off at a later time. So here we effectively apply two unit step functions. So first we switch it at time a and then we switch it off at time b. Let's look at the example. So first let's look at the sign which was switched at a given time at time 0. Well, then you would do as expected, right? You have the switched sign at time 0, so you ignore the thing which was before time was 0, so for negative time, but otherwise it's just a normal sine function, right? So just sine of t. Now, if instead we want to switch it at a later time and then switch it off again at even later time, then we have that expression. So we switch sine at a given time and then we switch it off at a later time. So here we have pi over 2. So that would be how your sine function would look if you wouldn't switch it off or on. And on top of it, you introduced a unit step function which switches on at this time, stays on until it reaches another time, and then it disappears. Okay, so that is 3 pi over 2. So it only lives between these two times. And so you see that if you do that, the only time it is not zero is when it is between these two times. And that is exactly that function, right? So sine multiplied by the difference of two unit step functions. And now let's try to again look at the sine, but which is switched on at a given time, switched on at a later time, but also shifted or delayed. So again sine, but this time note the difference, there is a shift inside the sine. And then you see that you had this sine which is shifted, and therefore then you apply the unit step function, which again selects only a window between these two times. Right? This is the unit step function with a difference of two unit step functions. And this is the sine. When you multiply them, you get a continuous function which switches on, stays on for a while, and then switches off. So this hump. So that what is an example of a causal function which has a direction in time, that something happens, and that will be needed to analyze more difficult ordinary differential equations in the future.